Hi, welcome to calculus class. We are going to learn about doing word problems involving integration today, integration applications. We're going to be working some problems that are actual AP problems from the AP exam. So most of our problems are going to all be using a calculator, and we're going to focus on developing some calculator skills as well as learning how to solve these problems. Our first problem says, traffic flow is defined as the rate at which cars pass through an intersection measured in cars per minute. The traffic flow at a particular intersection is modeled by the function f defined by f of t equals 82 plus 4 times the sine of t over 2 for t values from 0 to 30 inclusive, where f of t is measured in cars per minute and t is measured in minutes. Question A, to the nearest whole number, how many cars pass through the intersection over the 30-minute period? Okay, so this is a very common kind of a problem. The first thing I always do when I'm looking at a problem like this is I'm going to go into y equals in my calculator and type in the function that they give me. So I'm going to go 82 plus 4 sine of t, which I'm using x, divided by 2. Close the parentheses. Okay? So if you enter it into y1 at the beginning of the problem, you should only have to enter it once and be able to use it for all your calculations in the problem. So you want to enter it carefully and double check to make sure that it matches. This is a trig problem. We definitely need to be in radian mode. And that's the default setting for your calculator. So we always stay in radian mode in calculus unless explicitly told otherwise, which rarely ever occurs at all. So we're wanting to know how many cars pass through the intersection, but this equation gives us cars per minute. Okay, so we don't just plug 30 into this and solve, because that is not, this is a rate of change of cars over time. So I want you to consider what units would be the integral of this equation. And the way you figure out the units for the integral is you take the units for the y value, f of t or f of x, whatever, which is cars per minute, and you multiply it by the units for the independent variable, which is time, here measured in minutes. Notice the minutes will cancel and you'll be left with cars. So when you integrate this, you get the number of cars, okay? And so it's always valuable to double check and say, oh, if I were to integrate this, what would that answer units be? Because they're usually going to ask you one like that. So we want to find the integral of this over this whole 30 minutes from time 0 to time 30. So on my calculator, I'm going to go to my home screen and I'm going to figure out what is the integral from 0 to 30 of f of t dt. And you do have to write this down on your paper for your AP exam. Anytime you take an integral, you're allowed to use the calculator to do the integral, but you have to write down what integral you calculated. So we're going to go on the home screen, alpha window, option 4 for function integration. Lower limit 0, upper limit is 30. And then I've already got my function in here, so I'm going to hit vars, which is this button right here next to the clear button, stands for variables. And then I'm going to go to y vars, function 1 for y1. So that pulls in the function I've already typed, so I don't have to type it a second time. And then I just go dx and press enter, and it gives me the answer. Now, normally we round to 3 decimal places, but for this problem, it says to the nearest whole number. So it's just going to be 2,474. Now, keep in mind, you do not have to put units on your answer unless you're explicitly told to do so. We're not explicitly told to do so, so we don't have to. If you do put units on it, units are considered part of your answer and they will be graded and along with your answer, the units and the answer would both have to be correct to consider your answer correct. So I would recommend not putting units on the answer unless you are told to do so. All right, part B says, is the traffic flow increasing or decreasing at the time t equals 7? Give a reason for your answer. So you have a note card that says increasing and you have a note card that says decreasing. And so you might want to refer to those if you don't remember what those say real easily. You need to be studying those note cards so that you're ready for your AP exam. At least the whole stack once a week at this point in the year for sure, maybe twice a week. But increasing, the way you figure out if something is increasing is you take the derivative and find out whether if the derivative is positive, it's increasing. If the derivative is negative, it's decreasing. Okay, so we want the derivative of the traffic flow equation. This is the traffic flow equation. So I want to know, is this f prime of t positive or negative? So I'm going to go into my calculator and I'm going to hit second and then alpha window, and then option 3 for n deriv, and then I want ddx of, and then I'm going to hit vars, y vars, function 1. So I've got my function pulled in just like I did before. And we're wanting it at t equals 7, so such that x equals, and type a 7 in here. Oh, and right here I should not have f prime of t, I should have f prime of 7. Sorry about that. So now I'm going to press enter, and I get negative 1.873. That would round to negative 1.873. So is it increasing or decreasing? Decreasing. And why? Because f prime of 7 is negative. You can write is negative in words, or you can just do less than 0, which is a mathematically symbolic way of saying negative. Either way is fine. But that's the reason. Whenever it tells you to give a reason for your answer, you want to think, do I have a note card of this? Because that's what they're looking for, is do you know the properties that are on your note cards? Definitions, formulas, all that stuff. Okay, C, what is the average value of the traffic flow over the time interval from 10 to 15 indicate units of measure? So you have a note card that says average value on it, and that's the 1 over b minus a times the integral from a to b of f of x dx. That's what that note card is. Again, be studying your note cards. So that this is your a and this is your b value. A is always less than b, and those are going to be your the limits on your integral for your independent variable. So we're going to go 1 over 15 minus 10 times the integral from 10 to 15, and it's the average value of traffic flow, so we want the traffic flow equation right here, which is the capital F of t dt. And then we can use our calculator to compute this value. So I'm going to go back to my calculator and go alpha y equals number 1 to get my fraction, 1 over 15 minus 10, and then I'm going to go times the integral, alpha window number 4 for function integration, from 10 to 15 of, I'm going to pull my equation back in here, vars, y vars, function 1, dx. And there's my average value equation, so it's going to give me 81.899, rounded to the 3 decimal places. And then it says indicate units of measure. So when you're finding the average value of a function, it's kind of like finding the average of your grades. Its units are going to be the same as the units for the function initially. So the average value of traffic flow F of t was measured in cars per minute, so this is going to be measured in cars per minute. Okay. All right. Next, part D. What is the average rate of change of the traffic flow over the time interval from 10 to 15? Indicate units of measure. I really like this problem because it asks you average value and average rate of change in the same problem. So we have two note cards in your note card stack that have the word average on them, and you don't want to mix those up. So average value could be average any y value kind of unit. You could say average temperature, average population, average height, average, whatever. Could be anything. But when it says average rate of change, it's going to use those words, and that's when you switch to the other formula. And that's your slope formula. So you go, for traffic flow, the y values are going to be capital F of 15, that's y2, minus capital F of 10, that's y1, divided by 15 minus 10, okay? And we can do this in the calculator as well. We can go, see if I can get that to focus on there. Alpha y equals number 1 to get the fraction. I'm sorry, y vars function 1. So there's y1, and if I put parentheses 15 after that, it doesn't multiply times 15, it evaluates the function at 15. So that's just like saying f of 15. It's the same thing in your calculator when you do it like this. Minus vars, y vars function 1, evaluated at 10, divided by 15 minus 10. So this gives me 1.51, that's going to round to 8, okay? And then it says indicate units of measure. So for the units of measure, if you're ever confused about units, what I recommend that you do is do the math to the units that you just did to the numbers. So F of 15 was measured in cars per minute. So I had cars per minute minus another cars per minute over the bottom are these 10 and 15, which are our time units, which is measured in just plain minutes. So minutes minus minutes. So this would be cars per minute on top divided by minutes, which you could do times the reciprocal of minutes times 1 over minutes, which would equal cars on top of minutes times minutes, which would be minutes squared. So the units are cars per minute squared. So sometimes you can get some unusual units in calculus, and that's a good way just to figure out what they should be by doing the same math to the units that you just did with your numbers. All right, next problem. This problem says a tank contains 125 gallons of heating oil at the time t equals 0. During the time interval from 0 to 12 hours inclusive, heating oil is pumped into the tank at the rate h of t equals 2 plus 10 divided by the quantity 1 plus the natural log of t plus 1 gallons per hour. During the same time interval, heating oil is removed from the tank at the rate R of t equals 12 sine of t squared over 47 gallons per hour. So how many gallons of heating oil are pumped into the tank during the time interval from 0 to 12 hours? Okay, dropped my calculator. Before I jump into this problem, I'm going to clear my memory. Second plus 712. clear it all out. I'm starting a new problem. I don't want any of that old stuff in there. And I'm going to go to y equals, and there are two equations here. So I'm going to put them both in this calculator because I know I'm probably going to need to use them both, okay? And I'm going to put them in my calculator in the same order that they appear in the problem. So h of t is the first one and r of t is the second one. So I'm going to put h of t in y1 and r of t in y2. And that way I always know which one, y1 or y2, which function it is, because if it's the first one in the problem, it's y1, and if it's the second one, it's y2. So I don't have to look back at it each time. So I'm going to very carefully enter them one time, and I'm not going to have to keep entering them over and over again in the problem. So 2 plus alpha y equals number 1 to get my fraction, 10 on top of 1 plus the natural log of x plus 1, close the parentheses. And then the second one is 12 sine of x squared divided by 47. Okay, so I've got both equations in my calculator. I've checked to make sure they're right, and that way I'm ready to go. So part A says how many gallons of heating oil are pumped into the tank during the time interval from 0 to 12 hours. So this one is, h of t is the heating oil being pumped into the tank. R of t is the heating oil being removed from the tank. So if we're talking about how many are pumped into the tank, we're really only going to need to use the h of t equation. That's the only one relevant to the heating oil being pumped into the tank. So if I want to know how many gallons, and this is measured in gallons per hour, think about it. The integral is going to be the product of the units for the y value, which is h of t measured in gallons per hour, times the independent variable, which time is measured in hours. So if I just want to know gallons, I'm going to do an integral, okay? And this is a really common thing for them to ask us to do, as the first part A on the last problem as well. So we're going to integrate this function, h of t, the heating oil being pumped in, from the time 0 to 12. Those are given in the problem, dt. So now I'm going to go to my home screen, and I'm going to go alpha window, option 4 for function integration, 0 to 12. And h of t is my y1 because it's the first one that appears in the problem. So vars, y vars, function 1, dx. And then I'm going to press enter. And it gives me 70.57, that'll round to a 1. 70.571. And we don't need units because it doesn't say include units on the answer, so I'm not going to put them, and that's done. All right, B is the level of heating oil in the tank rising or falling at the time t equals 6. Okay, give a reason for your answer. Well, what we want to do is compare the rates that the heating oil is being pumped into the tank with the heating oil leaving the tank. So like if I figure out what the rate of heating oil coming in at 6 hours is, that's measured in gallons per hour, so h of 6, I'm just going to plug 6 in for my h function. That's going to tell me how many gallons per hour are going in at this specific time. And if I subtract from that the amount leaving, R of 6, so the amount being removed at the time 6 in gallons per hour, that's coming out. If this equals a positive value, then it's going to be rising because there's going to be more coming in than leaving. But if it's a negative value, then it's going to be falling because there's going to be more being removed at that time than coming in. So on my home screen, I can go vars, y vars, function 1, evaluated at 6, minus vars, y vars, function 2, evaluated at 6, and it gives me a negative 2.924. So since this came out negative, I'm going to say that the level of heating oil is falling. And it says give a reason for your answer. So I'm going to say because H of 6 minus R of 6 is negative. Okay, now that's not the only way that you could have answered that question. You could have also used like an inequality and compared these. Like if you add R of 6 to both sides of this inequality, you could say H of 6 is less than R of 6. Or likewise, you could have said R of 6 is greater than H of 6. All of that would be mathematically equivalent to what I just wrote down and would also be good reasons to support the answer. So you need to include that it's falling, and you need to explain how you knew that, which has to do with the rate going in being less than the rate of gallons per hour of oil being removed at the time 6 hours. Okay, C, how many gallons of heating oil are in the tank at the time 12 hours? Okay, so we want to actually know the number of gallons. So we need to consider how much we started with. It says that it has 125 at time 0. So we're going to have to add that on to the net change. So from the time 0 to 12, we're going to have to integrate the amount going in minus the amount coming out. And you could do that as separate integrals or all as one. It's mathematically equivalent. I'm going to do it all as one. 125 plus the integral from 0 to 12 of h of t minus r of t dt. So I'm going to type that in my calculator. 125 plus alpha window number 4, function integration, go from 0 to 12 of vars, y vars, function 1 minus vars, y vars, function 2 dx. Notice this is taking my calculator a minute to compute. You see it's scrolling right here? Sometimes it does that when the batteries are starting to get a little bit weak, which is why I strongly recommend that you put fresh batteries in your calculator before you take your AP exam, because your calculator computes faster with brand new batteries. So 122.026. All right, and that's all we need for that problem. All right, D says, at what time t, for time intervals from 0 to 12, is the volume of heating oil in the tank the least? Show the analysis that leads to your conclusion. Another way to say the least is saying it's at an absolute minimum. Okay, and we talked earlier this year about finding an absolute minimum by using the candidates test. So we're going to do that. That's the analysis. We're going to show the work for the candidates test for evaluating this answer. So the first thing we need to do is take the derivative of whatever it is we're trying to find that absolute min for. By the way, we would do the exact same thing if we were finding an absolute maximum. Take the derivative, set it equal to 0, and solve for the critical values. So what are we trying to find the absolute min of? The volume of heating oil. Well, the volume of heating oil equation is basically what we have right here on part C, okay? So the derivative of that equation is, well, the derivative of 125 is 0, and the derivative of an integral, those undo each other, so it'd just be h of t minus r of t equals 0, okay? So where does that equal 0? Well, I'm going to go into my calculator. To find zeros, I need to do that from the graph menu. So I'm going to go down to y3 and say vars y-vars function 1 minus vars y-vars function 2. And I'm going to go turn these other two off. If you go on the equal sign and press enter, it unhighlights it so that won't show on your graph. And you can then go back and click it back on at any time. And it's still in there, so like I'm still pulling the y1 into this one and the y2 into this one when you do it this way. It's just only going to show the one that's bold on the graph. So I'm talking about from 0 to 12 here. So I'm going to go into my window and say my x-min should be 0 and my x-max should be 12. And I'm going to hit graph. And I'm looking for where is this 0. So there's one, there's another. The x-intercepts are what I'm looking for. So I want to find those. Okay, so I'm going to go second and hit the trace button for the calculate menu and choose option 2 for 0. I have to go left bound, so I'm cursoring to the left side of this x-intercept, press enter, makes a little arrow here saying I'm going to look here. Cursor to the right side of the 0. I need to make sure these y values are now negative so I know I'm on the opposite side of the x-axis. Press enter. It kind of looks like a little bow tie here. It's saying I'm going to look between these two arrows for your 0 because it can only find one at a time. And then guess, I'm just pressing enter a third time. And then here's my first 0. 4.900515. Okay, so I'm going to put t equals 4.7900515. You cannot round down this answer because it's not the final answer to the problem, okay? Your calculator does, however, store that value as x for your next computation. So we might want to go ahead and start working on our table here since it's got that value stored so we don't have to type it in. We're going to have times on the top and we're going to have volumes on the bottom. And the times that we want to include are going to be the endpoints, so 0 will be the first one. And then here, our critical value, 4.7900515 will be the next one. And then we're about to figure out what that x-intercept is, so we'll have another one that we have to use the calculator to compute. And then the endpoint of 12 will be the other one. So we want to know what the volume is. Well, the volume at time 0 is 125. They gave us that in the problem to start with. But now we need to figure out what the volume is here. So the way that we do that is by using this equation that we just wrote down in part C. We're going to go to the home screen and go, wait a minute. I can actually just hit second enter, second, and then the enter button to pull this back up again. And this will be the same equation except for instead of going all the way to time 12, I just want to go to this time. So I'm going to cursor back over here where my 12 is, hit the clear button, type X because it stored this number, 4.7900515. It stored that value as X when I computed the x-intercept here just a moment ago. So I'm going to press enter. And again, it's taking its little sweet time, but it gives me a volume of 149.408. Okay, that's the volume at that time. Oh, and we already have the volume at time 12 because that's what we found on part C. So that's 122.026. We just have one more little piece of our table to compute the values for. So going back to the graph, I want to find this x-intercept. Second, trace button for calculate. Option 2 for 0. I'm going to scoop my little cursor just to the left side of my 0, my x-intercept. Press enter. Scoot it to the right. Press enter. Press enter when it says yes. And here's my next time value that's a critical value, 11.31847. And now I need to compute the volume at that time. So I'm going to go second quit, and I'm going to press second and then the enter button down here at the bottom, which pulls up the exact same thing that I just had. And guess what? I don't even need to change anything because this x value is now stored to be the more recent x-intercept that I used my calculator to compute. So I'm just going to press enter and it's going to give me a different answer, which is going to be the amount of heating oil at this new time of 11.31847. So that's going to be 120.738. All right. Oh, and I forgot. If I make this look the same, I didn't write the time here. I probably don't need to do that since it's over here, but in the interest of having it look completed, I'll do that. So we are looking for the absolute minimum volume. So these are the volumes. So which volume is the very least? Well, it's this one. But is that what the answer is? At what time is the volume of heating oil the least? So the time that it is the least is 11.31847. This unboxing is the answer. Okay? And the analysis that leads to the conclusion is the work that we have shown right here. The only thing that I did not include in the work is this equation right here that I used to find the volumes, which normally you do need to include that. 125 plus the integral, I'm going to put from 0 to t, so I only have to write it once and not for each time that I have in my table, of h of t minus r of t dt. And that way they know how I came up with these volume values. The only thing is, since that was the exact thing I did in the last part, that's the reason I didn't write it here. But it would be a good idea to include that in your work for your table. Okay, moving right along. The next problem is from a graphical standpoint. It says a car is traveling on a straight road with a velocity of 55 feet per second at the time t equals 0. For time values from 0 to 18 seconds, the car's acceleration a of t in feet per second square is the piecewise linear function defined by the graph above. So this is the acceleration graph, a of t. Is the velocity of the car increasing at t equals 2 seconds? Why or why not? All right, well, let's kind of familiarize ourselves again with these motion problems. We've talked about that somewhat recently, but if you have a position equation or graph, whatever, the derivative of position is equal to velocity, and the second derivative of position is the first derivative of velocity, which is the acceleration. The integral of acceleration is velocity, and the integral of velocity is position. Okay, so those are very important things that you need to kind of have readily available anytime you do one of these position, velocity, acceleration kind of problems. So we're wanting velocity, but we have acceleration. So how's that related? Well, the acceleration is equal to the derivative of the velocity. So we're talking about at the time 2 seconds. Is the velocity of the car increasing? So what is, oh, well, if the velocity is increasing, that means its derivative is positive, right? So the derivative of the velocity is equal to the acceleration. So we just need to figure out whether this is positive or negative. A of 2. What is A of 2? 15. Well, that's positive, so that means it's increasing. Think about your increasing note card. The derivative is positive, it's increasing. Derivative of velocity is acceleration. So you just need the sign of the acceleration. Okay, B. At what time in the interval from 0 to 18 other than t equals 0 Is the velocity of the, that should say car, not car 55 feet per second? Why? Okay, so the velocity is 55 feet per second at the time 0. Where else is it going to be the same? Well, we have all of this positive acceleration, which is making the velocity increase till we get here. Then we have negative acceleration, which is making it decrease. So when the increasing and the decreasing balance out and are equal, we should be back to the same velocity we began with. So if you look here at this graph, there's some symmetry here. It looks like this trapezoid piece up here, and then it looks like a similar shape on this bottom side, except it just extends further. But if you notice, like this triangle here looks congruent to this triangle here, and then there's 3 squares here, 3 squares here. So it looks like when it gets to 12, all this that was added on is then subtracted off. So I would say at time 12, it's going to be back to the same, because that's where the integral, which is the area between the curve and the x-axis, would be equal to 0. The integral from 0 to 12 of a of t dt is equal to 0. And that's my reason why. It balances back out. All right, part C. On what time interval from 0 to 18, on the time interval from 0 to 18, what is the car's absolute maximum velocity in feet per second? And at what time does it occur? Justify your answer. All right, this problem is a lot like the last problem, part D, that we did. So I recommend that you pause your video and then try to do this problem on your own, and then come back to check and see if you got it right. So I'm going to assume that you have done so. So we want to find the absolute maximum velocity. So we want to first take the derivative of the velocity, which is the acceleration, and set it equal to 0. And that's how we'll find the critical values. So we'll have a table with times, and we're trying to find the maximum velocities here. Starting with 0, at time 0, the velocity is 55. That was given in the problem. And then we need to find the zeros of the acceleration equation. So that's 6 and 16. T equals 6. Wait, I don't need to write t equals. I got time on the side there. So I'll put 6 and 16. And then the ending time is 18. So we need to know what are the velocities at those times. So we're going to have to do an integral for those. So the velocity is going to equal the starting velocity, which is 55, plus the integral from 0 to whatever time we're going to of a of t dt. And that's how we're going to compute the values that go here. So for v of 6, we're going to say, well, what is all this integral equal to, which is just finding the area, and add it to 55. Okay, so what is this? It's the area of a trapezoid, so you can do base 1, which is 6, plus base 2, which is 2, 6 plus 2 is 8, times the height, which is 15. So 8 times 15, this is a calculator problem, so clear my memory. 8 times 15 divided by 2 gives me 60. And then I'm going to take the 60 and I'm going to add it to the 55 here. So that's going to give me 115. Okay, now at 16, I got to take my 60. I'll go ahead and write this on here so I don't have to think of it again. And then I'm going to figure out this trapezoid's area. So the base is 2, 4, 6, 8, 10, plus 2, 4 is 14. 14 times the height of 15 divided by 2 is 105. But keep in mind this is negative 105 because it's under the x-axis. And y'all, I'm using the area of a trapezoid formula, which you should know, base 1 plus base 2 times the height divided by 2. That's what I'm using to find the areas. So if you don't know that formula for area of a trapezoid, it's definitely required that you know that one on the AP exam, because if you remember, we did areas of trapezoids with Riemann sums too, and they're not going to give that to you. So add it to your note card stack if you're not familiar with it. Now I'm going to take my negative 105 and I'm going to add it to my 55. Oh wait, plus the 60. Okay, so we got 60 minus 105. Whoops, I pressed decimal instead of 0. Plus the 55 we started with. So that comes out to 10. So I filled that value in my table. And then the last one for 18, I've got to figure out, this is 2 times 15 is 30. This is base times height divided by 2 is 15. So just to add 15 to what I had here, 15 plus 10 is 25. Okay, so what's the absolute maximum velocity and at what time does it occur? And it doesn't say include units, it gives you the units in the problem. So I'm going to say the biggest is at time 6. So at time 6, the velocity is 115. So that's the answer. And the justification is the work that I have shown right here. All right, D. At what times in the interval from 0 to 18, if any, is the car's velocity equal to 0? Justify your answer. Well, it starts at 55, and then it increases to 115, and then it decreases all the way down to 10, which looks like that's the absolute minimum, and then it goes back up to 25. So if this is the absolute minimum, does it ever equal 0? No, the lowest it goes is 10. So I'm going to say no, and the justification is the absolute minimum velocity equals 10 feet per second. So it doesn't get down to 0 if its lowest it goes is 10. For this problem, this one did not come from an actual AP test, but it was written by a woman who helps write the AP test. So it is very aligned with the level of rigor that you'll see on the AP exam. This one says the rate at which water is being pumped into a tank is given by the continuous increasing function R of t. A table of selected values of R of t for the time interval from 0 to 20 minutes inclusive is shown below. And so we see 0 for 9, 17, and 20 for times in minutes, and then the R of t values for gallons per minute are 25, 28, 33, 42, and then 46. Okay, it says use a right Riemann sum with 4 subintervals to approximate the value of the integral from 0 to 20 of R of t dt. Is your approximation greater or less than the true value? Give a reason for your answer. So the first step is to do a right Riemann sum. When you do your Riemann sums, you have to show your work, even though it's arithmetic, okay? So you're finding the areas of the rectangle. So the width of the rectangle is going to be the difference between consecutive time values. So 4 will be the width of the first rectangle. And then the height of the rectangle is going to be given by the y value. And if it's a right Riemann sum, then you choose the y value on the right of that interval. So we are not going to use the 25 at all. We're going to use the 28 for the first rectangle's height. The next rectangle will be from 4 to 9 for the width, so that's a difference of 5. And then the height is 33. And then the next one is from 9 to 17, so that's going to be 8. And then the height for that one will be 42. And the final one is from 17 to 20, so that's a width of 3, and then the height is 46. So I used the 28 for the first one, the 33 for the second one, the 42 for the third one, and the 46 for the last one. I did not use the 25 at all. If I had done the left Riemann sum, I would have used the 25, then the 28, then the 33, then the 42, and not the 46 at all. Okay, so got to read it carefully to see which type of Riemann sum that they want. Okay, so you can compute this. This problem doesn't tell you whether it's with a calculator or not. I'm going to go ahead and use one. Most of the problems for integration applications are done with a calculator. So 751 is what that comes to. That's our Riemann sum approximation of this integral value. Now, is our approximation greater than or less than the true value? All right, well, it says up here that this is an increasing function. So if the function is increasing and we're choosing the value on the right as the height of each rectangle, what you're going to see is that the rectangles end up being above the function. And so you're going to have a value that is greater than the true value. And the reason is because r of t is increasing. Okay, if it was a decreasing function, then the right Riemann sum would be less than the true value. Okay, and then of course if it was a decreasing function, you'd have to take that into consideration. Sometimes it's helpful to draw a picture, kind of like the way we did on our Riemann sums lesson day. Okay, part B. A model for the rate at which water is being pumped into the tank is given by the function w of t equals 25 times e to the power of 0.03 t, where t is measured in minutes and w of t is measured in gallons per minute. Use the model to find the average rate at which water is being pumped into the tank from the time 0 to 20 minutes. Now, average rate at which water is being pumped into the tank. This is a model for the rate at which water is being pumped into the tank. So they're wanting the average value of this function. Okay, it looks really close to average rate of change, but if it's average rate of change, it's actually going to say average rate of change. So this is not average rate of change. This is the average value of the rate at which water is being pumped into the tank. So we're going to do the 1 over b minus a times the integral from a to b of f of x dx formula, which is one of your note cards. So 1 over 20 minus 0 times the integral from 0 to 20. These numbers are coming out of the problem, of w of t dt, and then we're just going to go into our calculator and type in the w of t function, 25 e to the power of 0.03 x, and so then on the home screen I'm going to go alpha y equals 1 over 20 times alpha window. Function integration is number 4. The integral from 0 to 20 of window, go back in that little parentheses there. Vars, y vars, function 1 dx. 34.255 would be the answer. All right, part C. The tank contained 100 gallons of water at the time t equals 0. Use the model given in part B to find the amount of water in the tank at the time 20 minutes. So you start with your starting value and you add to it the integral from 0 to 20 of that model, W of t dt. So real similar to what we just did here, but not 1 over 20. We're going to go 100 plus alpha window number 4, 0 to 20 of vars y vars function 1 dx. 785.099. All right, we're on to the last problem that we're going to do prior to your assignment. And it says car A has a positive velocity V sub A of t as it travels on a straight road where V sub A is a differentiable function of t. The velocity is recorded for selected values of over the time interval from 0 to 10 seconds as shown in the table below. So we have time in seconds, 0, 2, 5, 7, and 10. And then the velocity is measured in feet per second, and that goes 0, 9, 36, 61, 115. So it says, A, use the data from the table to approximate the acceleration of car A at the time 8 seconds. Indicate units of measure. All right, 8 seconds is not in the table. That's between 7 and 10. And this is velocity, and they're asking about acceleration, but it's an approximation for acceleration. So I want you to remember that v prime of t, the derivative of the velocity, is equal to the acceleration. We don't have an equation that we can take a derivative of, but it also, derivative means slope, and we do have 2 points, so we can use the slope formula for it, and that will allow us to approximate the acceleration at this time. So I'm going to go y2, which is 115, minus y1, which is 61, divided by x2, which is 10, minus x1, which is 7. So we can do this in the calculator. 115 minus 61 gives us 54. Divided by 3 is 18. And it says indicate the units of measure. So we can always do the same math to the units that we just did to the numbers. This is feet per second minus feet per second, so the numerator is feet per second. And then in the bottom we have seconds minus seconds. So it's feet per second divided by seconds, or times 1 over seconds. So that's going to be feet per second squared. Okay, part B. Use the data from the table to approximate the distance traveled by car A over the interval from 0 to 10 seconds by using a trapezoidal sum with 4 subintervals. Show the computations that lead to your answer and indicate the units of measure. Okay, so this is a velocity function, and total distance traveled is going to be the integral of your velocity. So to do an integral, you need a function, but we're going to use a trapezoidal sum with the data in the table to approximate the integral. And it does say show the computations, but even if it didn't say that, you always have to show your work on any Riemann sum. So remember your formula for the area of a trapezoid. Base 1 plus base 2 times the height divided by 2. Because we're going to, oops, I don't have that on there very good. Okay, we're going to have to do 4 trapezoids. So the first trapezoid will have, remember the bases are the parallel sides, which are the y values. So we're going to go 0 plus 9. And then the height is the distance between the two x values. So that's times 2, and then divided by 2. Because of the formula for the area of a trapezoid, you divide by 2. Plus, the next trapezoid is going to be adding the 9 plus the 36. Then multiplying that by the difference between these consecutive x values, so that's 3 divided by 2. Plus the next one is going to be 36 plus 61 And then we'll subtract the 7 minus 5 to get the height, so that's 2, and then divided by 2. And then finally we'll add 61 plus 115. Multiply that by, pardon me, 3, and then divide by 2. And that's what we're going to type in the calculator to find the approximation for the total distance traveled by the car A from time 0 to 10 using our trapezoidal sum. So let's see, these 2's are going to cancel out. So this is going to be 9 plus 36 times 3 halves, or 1.5, plus these 2's cancel out. So it would be 36 plus 61, plus the next one is going to be 61 plus 115 times 1.5. 3 halves is 1.5. So this is equal to 437.5, and it says to indicate the units. So remember, whenever you're doing a Riemann sum, it's like multiplying base times height, units. Feet per second times seconds. Feet per second times seconds. Notice the seconds cancel out and we're just left with feet. Okay? Which also makes sense for total distance traveled. How many feet did it travel? Okay, C. Car B travels along the same road with an acceleration of a sub b of t equals 2t plus 2 feet per second squared. At the time 3 seconds, the velocity of car B is 11 feet per second. Which car is traveling faster at time 7 seconds? Explain your answer. Okay, well, the velocity of car A at 7 seconds is given in the table. It's 61 feet per second. So that is a given. We don't have to figure anything out there, but we have to compare it to the velocity of car B, okay? And we don't have the equation for velocity, but we do have the equation for acceleration, okay? So we can integrate the acceleration equation, 2t plus 2 dt, to get the velocity equation. And notice they tell us at the time 3, the velocity is 11. So we can use that point to find the c value after we integrate. So let's try that. Let's do power rule backwards. So I'm going to add 1 to the power on the t. That's going to be t squared, and then multiply by the reciprocal of the new power, 1/2. 1/2 times 2 is 1. So now my coefficient is just 1. Plus, integrating the 2 is going to give me a 2t, and then I have my plus c. So they tell me my velocity is 11 when my time is 3. So if I sub in a 3 for t and an 11 for velocity, I can solve for what that c value is. So I have 11 equals 9 plus 6 plus c, and that means 15 plus c. If I subtract 15 on both sides, then I get -4 equals c. So the velocity equation for car B is t squared plus 2t minus 4. So if I want to know what the velocity of car B is at time 7 to compare with the velocity of car A at time 7, I'll sub in a 7 for my time here. And that's 49 plus 14. Take 4 away. Well, 14 minus 4 is 10. So 49 plus 10 is 59. So, and this is feet per second. It says which car is traveling faster at the time t equals 7 seconds. So we're comparing them. 61 for car A, 59 for car B. So car A is traveling faster, and it says explain your answer. The work that we have shown to calculate those values is the explanation. So we are done with this lesson on integration application. So good luck with your assignment. Sometimes it's a good idea to work with a buddy on these kinds of things and talk it out. You grow a lot as a learner when you work collaboratively, so I would encourage you to do so, especially if you are having any trouble. Also, feel free to contact me if you need any help at all, and have an absolutely wonderful day. Bye for now.